So much of pre-calculus is about how do we transfer our understanding of a function that comes from its formula into understanding of that function which comes from its graph. This section is a lot about that, because in this section we ask the question, how are simple changes in the graph of a function, changes in its shape, its size, its orientation, reflected in the formula for that function? And the kinds of basic changes, simple changes we're going to talk about, come in three flavors. Shifts of a graph that move its location within the xy plane but do not change its shape, size, or orientation. Stretches that can make a graph wider or possibly taller or shorter or narrower but don't otherwise change its location or its orientation. And finally, reflections, which can reflect the entire graph about a horizontal axis of symmetry or a vertical axis of symmetry, but otherwise don't change the size, the shape, or the location of the graph. We'll start with shifts. So say I have the graph of a function. This is the graph of a cube root function, y equals the cube root of x. If I decided to shift this graph up by 2 units, then I would see that the entire graph just moves up. Every point from the old graph now appears 2 units, exactly 2 units above its old location. What happened to its formula? Well, that 2 is reflected in the formula for this new graph by being added to the outside of my function. So addition on the outside of my function seems to have the effect of shifting my graph vertically, either up or down. Meanwhile, if I wanted to shift my graph from side to side, I should still add and subtract, but not add and subtract to the formula for the function on the outside, but add and subtract directly to the value of x on the inside of my function. For example, here I've shifted my graph 4 units to the right. And when I shifted the graph 4 units to the right, notice what happened to my expression that defines my function. I've taken that 4 and I've subtracted it, interestingly enough, from the value of x. So how are we going to keep all of this stuff straight? What we notice is that any kind of shift, regardless if it's a horizontal or a vertical shift, happens with the same kind of arithmetic. It always involves addition or subtraction. For a horizontal shift, we accomplish a horizontal shift by replacing x in my function by x minus the amount that I want to shift to the right. X minus 4, for example, shifted my graph to the right by 4 units. If this were x minus negative 4, x plus 4 in other words, I would have shifted the other direction, shift to the left. Same thing with my vertical shifts. I can accomplish a vertical shift upwards by subtracting the appropriate amount from my y variable, or I can do it the way that we showed in the graph app, which is to add directly to the outside of the function on the right-hand side of the equation, and that has the effect of shifting the graph up by that amount. So that closes the book on shifts. What about stretches? To accomplish a stretch of my graph, I just want to use a different kind of arithmetic. Where shifts use addition and subtraction, my stretches are going to use multiplication and division. Let's think about the horizontal version of this stretching first. So let's suppose that I were to take the x in my expression here and replace it by 5 times x inside of my expression. So what's happened? It looks like I've taken all the points on my original graph and I've just cut their x coordinates in a fifth, right? I've multiplied all their x values by 0.2. And what that does is it has the effect of sort of compressing the whole graph horizontally in towards the y-axis by a factor of 5. If I wanted to stretch it out by a factor of 5, I would just multiply the x in place here by 0.2. And that would have the effect of stretching it out by a factor of 5 away from the y-axis. So multiplying my x variable, replacing x by a multiple of x inside of my function, has the effect of a horizontal compression or stretch. And if I wanted to do that vertically, I would just do it to the whole expression, or equivalently do it to the y value instead. For example, if I multiply on the outside of my function by 3, I've now stretched all of the points on my graph 3 times further away from the x-axis than they originally were. And if I multiply by 0.3, or 0.2, let's say, then I've compressed all of my points toward the x-axis by a factor of 0.2, which is the same as a factor of 5. So what all stretches of a graph have in common is that they involve multiplication or division instead of addition or subtraction. If I multiply in place my x variable by a number a, that's going to affect a horizontal compression towards the y-axis if a is greater than 1, or if a is between 0 and 1, it's going to stretch all of my points horizontally away from the y-axis. Similarly, if I multiply my y in place by a number y, or a number a, it's going to compress everything towards the x-axis by a factor of a, a vertical compression, or stretch away from the x-axis if the a is between 0 and 1. But usually that's not the way that we visualize it. We usually visualize it by operating on the outside of the function f of x on the other side of my y equals f of x equation. And that has the effect of reversing our intuition. If I multiply on the outside of my function by 4, I'm going to stretch vertically the graph of that function by a factor of 4. I would compress it, again, towards the x-axis if the thing I multiplied by was between 0 and 1. And so if that takes care of the shifts and the stretches, what about our last class of graph transformations, the reflections? When the rubber meets the road, anytime we do analytic geometry, every reflection in mathematics at the end of the day comes down to multiplying something by -1. Why? Because what happens when you multiply something by -1 twice? We get back to +1, which is the same thing that we started with. So -1 is this magic reflection factor, this magic thing we can multiply by to reflect a graph. So as you might expect, if I wanted to reflect this graph horizontally, I would take my x quantity on the inside of my function, just multiply that x by -1. Sure enough, what I get is a graph that has been reflected horizontally. In other words, reflected across the y-axis as the axis of symmetry. And the same thing would have happened in this graph's case. You actually can't tell the difference between the results. But if I multiply the y by -1 instead, what I get is a vertical reflection, a reflection across the x-axis as opposed to a reflection across the y-axis. For this particular graph, it has a high order of symmetry so that we can't actually tell the difference between the horizontal and the vertical reflections. But there are other graphs. This graph, for example, is the graph of y equals x to the third minus 4x squared. If I apply a horizontal reflection by replacing x by -1 times x, I get a graph that looks like the one over here on the left. Whereas if I apply a vertical reflection by replacing y by -y, I get a graph that looks very different. So reflections are accomplished by multiplying either the x or the y by -1. As you might expect, multiplying by -1 in the x variable accomplishes a horizontal reflection, a flip over the y-axis. And multiplying the y by -1 effects a vertical flip over the x-axis, which is the same as either replacing y by -y or replacing f of x by -f of x. This list of graph transformation individual steps can be glued together to create multiply transformed versions of any parent graph. So as soon as you have a graph that you know the basic shape of, you can use any combination of shifts, stretches, and reflections that you want to move it around and change its shape and orientation inside of the xy plane and get it into whatever shape, size, and orientation that you want it to have. And so this section is all about making the connection between those different steps of how they're reflected in the graph and then how are they reflected in the formula for these functions.